Hello students, so we are going to start with a new chapter, work, energy and power. This is lecture number 1 of this chapter. Well, the words are very common and we are using it in day-to-day life, right? Like you must have learned in lower classes about work done, types of energy. Okay, so in this particular chapter we are going to understand what is work done, what are the different kinds of energy, what is work energy theorem, what is potential energy, mechanical energy. We are going to discuss about the collisions, right? Okay, so before starting with the chapter, what is work done? In practice, practically speaking out, work done means, I'll explain with an example. Like if you are doing some homework, that is work done. Your father is working in an office, he is doing some work. Your mom is say cooking, she is doing some work. A lady is carrying some bucket of water and she is walking, it's a kind of work done, right? So these are all the practical examples of work done, right? Energy means ability of an object or a person of doing work, right? If there are two persons, right? If one is able to run 2 kilometers and the another is able to run 4 kilometers, and we will say that the another person is having more energy, right? He is more energetic. So capacity or ability of doing work is known as energy, right? Okay, power means the rate of work done, but in what amount of time is the work done, right? If I'm giving you a homework, right? So I have assigned the same work. One student had done the homework in 1 hour. The another student took 1 day for doing the same work. So the rate of doing work is different. That is what is power, right? We have used this word like power of this bulb is this much. Practically, power of electric motor is this much. So that represents the rate of work done. How fast is the object or the machine able to do work? That is what is power. Clear? Okay. So that was all related to giving you a practical examples. Now in physics, how to define work done? We'll first understand the concept of work, right? When force is constant, when force is variable, how can we calculate work done? First of all, how to define work done in physics, right? Suppose there is a smooth surface. There is a block having mass m. A block of mass m is placed on a smooth surface. Let us say it is at rest. It is not having any velocity. Clear? Okay. Now suppose I am applying a force F on the block in this direction. I have applied a force F on the block of mass m, and because of this force the block displaces and it reaches to a point, say B, from A, right? So the block has been displaced by an amount D when you applied a force F on the block, right? So work done can be defined as when force is applied on a body, and if it displaces in the direction of applied force, then work is said to be done. So work done can be mathematically or formula wise written as dot product of F and D. Definitely this you must have learned in your chapter vectors. We have seen that dot product of two vectors A and B is defined as magnitude of A, magnitude of B into the angle between two vectors A and B. Clear? Okay. Well, the another thing about the dot product is the result is always scalar. Right? So basically work done is dot product of force and displacement, right? So work done will also be a scalar quantity. In this case, F dot D, it can be written as F D cos theta. In our particular case, both force and displacement are in same direction. both force and displacement are in same direction. So theta will be equals to 0 in our case. So work done is F into D, cos 0 is 1. Right? This is the simplest way to find work done, right? Only when your force is constant, right? Okay, so we have seen that work done is actually the dot product of force into displacement. Further, we'll also generalize, or we'll make the definition of work done very precise. Okay. See, as you can see that work done depends on the value of force, displacement and the angle. It also depends on the angle. Now we know that cos theta can be positive, cos theta can be negative, cos theta can be 0. Accordingly, work done can be positive, work done can be negative, work done can be 0, right? Work done is a scalar quantity, as it is the dot product of two vectors. What is the unit of work done? So work done is FD, so it is Newton, displacement is in meter, or you can say it as joule. So the unit of work done is Newton, meter or joule. It is a scalar quantity, and work done also depends on angle. So work done can be positive, 0 and negative. Clear? Work done can be positive, can be 0, can be negative. We will see one example. See, in our case, let us discuss first case. When both force and displacement of the block, when they are in same direction, if I am applying a force on any object, and if it displaces in the direction of the applied force, then the angle between F and D will be 0 degree, right? So work done will be positive. Here, if force is applied at an angle of say 30, 60, then also work done will be positive. But in some cases, work done can be 0 when if theta is 90. Let us take one example. Suppose I am carrying some load on my head and I am walking in this direction. So my displacement is in horizontal direction, right? The force, the normal force acting on me will be in upward direction. You have seen in the chapter Newton's law of motion, normal is in upward direction, displacement is in horizontal direction. So the angle between F and D is 90, right? So FD cos 90, the value of cos 90 is 0. So work done is also 0. Clear? We can take one more example. Let us consider the case of uniform circular motion. In uniform circular motion, the displacement of the particle is in tangential direction. Force, centripetal force is towards the center. So the angle between these two is 90. So in such cases, work done on the object by centripetal force will be 0. Will be 0. Clear? Okay. So we have seen that work done can be positive, can be 0. Let us consider the case where work done is negative. For theta greater than like 90, let us say we will take an example of frictional force. If the block is moving in this direction, right, the frictional force will oppose the relative motion. It will oppose the relative motion, not the motion. So in this case, work done by the friction will be, the angle between frictional force and displacement is 180. So work done by frictional force will be force displacement into angle. Cos pi is -1. Clear? So work done is negative when friction is performing some work on the body. So we have seen work done is scalar quantity. It is dot product of F and D, right? The unit of work done is Newton meter or joule, and work done can be positive, negative as well as 0. CGS unit of work done is erg, right? And 1 joule is 10⁻⁷ erg. You can convert it by using kilogram meter square by second square, because joule is equals to kilogram meter square by second square, right? It is easy, you must have learned in your 11th standard. Okay, now let me define more precisely, right, what work done is actually. Now suppose if a force F is applied which makes an angle theta with the horizontal, suppose. And because of this force, block displaces by an amount, say d. In this case, work done is equals to, see now this is f, this is theta, this will be the component of f cos theta, this will be the component of f sin theta. So here f is not doing the work to move the block in horizontal direction, it is a component of the force which moves the block in horizontal direction, right? So the effective force will be f cos theta. So more precisely, work done is defined as the component of the force in the direction of displacement. The component of force in the direction of displacement into displacement. Clear? Here, make it very sure. Because of this force F, it is not moving from say A to B. The displacement d of this block is because of the component of force, that is F cos theta. So work done can be written as component of force in the direction of displacement into displacement. Clear? So this is, the result will remain the same. We will write f cos theta into d. So work done will be the same, right? But you can define work done more precisely as the component of force which displaces the block, right? Okay, since displacement is also a vector quantity, so we can define the work done in either way as component of displacement in the direction of force into force. Right? Both the ways are correct, both will give you the same answer. Here I have taken the component of force in the direction of displacement. In few cases, we need to take the component of displacement in the direction of force. Right? So either you write it as component of force in the direction of displacement into displacement, or component of displacement in the direction of force into force. Right? So this were all the different definitions of work done. Right. We have seen the formula to calculate work done, f d cos theta, dot product f and d. Of course, it's a scalar quantity. Now, in the next video, we will solve how to calculate work done if force is variable. That is, if force depends on x position, depends on say time. That is, if force is continuously changing and we are said to calculate the work done, then how to calculate it, we'll say this in the next video.